For section 5, we're going to get into a little bit more with those square roots that we were talking about with completing the square, but we're going to talk about something called complex numbers and roots. So this is when I talked about this briefly at the beginning of the year, where we had, like with the quadratic equations and the graphing, I said that there's options for you to have like the graph hit the x-axis 2 times, or it can hit it 1 time, or it can hit it no times. And if you remember when we talked about that, this would have been in section 3? Right here. We looked at this chart together and we said that you can have one solution because the graph hits the x-axis like at the vertex. You can have 2 solutions because it hits it twice, or this key word here, no real solution. And I kind of alluded to the fact that we'll talk about that case later. Well, it's later. Okay, so now we're going to talk about it. So we're going to be going over like what happens in this case when it doesn't hit an x-axis and it's no longer considered real numbers. So this is when complex numbers come in. And we're going to talk about something called the imaginary number today. So if we look at these 2 examples, they look fairly similar. You have x squared equals 4 and you have x squared equals negative 4. Previously, like if we were using our square root property, we would have done the square root on both sides. And so for this first one, you guys would have had x equals plus or minus 2. Okay, fairly simple. We've done that before. Now in the second one, if I square root both sides, I'm going to get x equals, and it's not going to work. Okay, if you have a calculator in front of you and you wanted to test this, if you tried to take the square root of a negative 4, your calculator will not do it. It'll give you an error message of some sort. Just like if you try to divide by 0, your calculator won't do that either. There's certain things that your calculator can't do because it's not considered to be a real number. It's considered to be imaginary. So we can't find the negative square root of numbers. We can't find the square root of a negative. Because essentially you're trying to take x squared, so you're trying to take it times itself. So it has to be the same number, same sign. And there's no way I can do that with 2 positive numbers and 2 negative numbers to get something to come out negative. One has to be negative, one has to be positive, but that's not what's happening here. So the imaginary unit is using the letter I, and it's a lowercase I to represent the imaginary number. And what that represents is anytime that you see a negative underneath the square root sign, if I wanted to simplify it, I'm going to have to pull out the imaginary number I. So I really represents the square root of negative 1. So a lot of times if you have a negative number underneath your square root sign, what we'll do is just pull out the negative piece on its own to kind of isolate that imaginary piece, and then work with our positive number that we have now like we would have done previously. So for example, if I have something like that square root of negative 4, what this really means is I could split this apart so that it says the square root of 4 times the square root of negative 1. Just like when we were reducing square roots the first time, I was able to kind of take them and break them apart and split them. I can do the same thing here to get that positive and that negative piece. Now when I do that, the square root of 4 is a 2, and the square root of negative 1, using this piece up here, is the I. So this answer would be 2I. Technically, it could be plus or minus 2I. For right now, just kind of getting used to using the imaginary unit, I'm not going to worry so much about putting the plus minus in front. Okay? For number 2, we have the square root of negative 5. Now, 5 is not a perfect square number. So what I'm going to do, again, similar to what I did on number 1, I'm going to split it apart so it's the square root of 5 times the square root of negative 1. I can't do anything to the square root of 5 because it's not a perfect square number, and the smallest perfect square number is 4, and that can't go into 5 at all. So I'm going to go ahead and just leave this as the square root of 5. But the negative I here, or the negative 1, that comes out as an I, so it just attaches to the end. So the square root of 5i. Another way you might see it written is I square root of 5. They might just switch it around. A lot of times if we do that, if it's just a square root, you will probably see it written this way instead. Just because sometimes if it's not in front of the square root, the I can get sometimes lost or dropped by somebody by accident. So sometimes we like to put it in front so that we make sure it doesn't get forgotten. All right, if we take a look at number 3, we have the square root of negative 12. So again, I would just split it apart so you've got the square root of 12 times the square root of negative 1. Now with 12, we can break this one down a little bit more because there is a perfect square number that can go into 12. So I could rewrite this as 4 times 3, because 4 is a perfect square that goes into 12. And then that square root of negative 1 is just going to be an I, so I'm going to have an I attached. So remember what we were doing before with those square root problems. The square root of 4 is going to be a 2, so 2 comes out of the square root sign. And then you still have this square root of 3, because 3 can't do anything. It's got to just stay in that square root. And then we have times I. So to kind of finish it out, this is when I said sometimes I is going to get brought up to the front. So it's going to say 2I square root of 3. We've seen ones like 4 with fractions before, and just like with multiplication, how you can separate them out. Like I could have, on that second step up there, I could have written square root of 4 times the square root of 3, like I could have separated them out. You can do that with division. We've talked about this before. So I could rewrite this as the square root of like negative 4. I just have to pull that negative somewhere over the square root of 25. It could have been a negative 25 instead if you wanted. That negative sign just has to attach to one of the numbers. It doesn't matter which one. If I attach it to the 4, I'm going to go ahead then and write it as the square root of 4 times the square root of negative 1 all over the square root of 25. Okay, so what would be the square root of 4? 2. The square root of negative 1 is that's your imaginary unit, so I. And the square root of 25 would be 5. So 2I over 5. All right, let's turn the page over. Why don't you guys try number 5? So if you guys started by splitting it apart, so you have the square root of a positive 40 times the square root of negative 1. You don't have to do this step. If you guys know that there's just going to be an I that comes out, you don't have to split it. But until you guys start to understand what that negative 1 really represents, I would split it apart like this so that you're just working with a positive number instead. Especially as we're just, I mean, this is brand new to you guys. So I don't want you to just jump in and think that, you know, you have to do it the fastest way. Take your time with these. What's the perfect square number that goes into 40? Good. So I would write that as 4 times 10. Remember those perfect square numbers from yesterday are like 4, 9, 16, 25, 36. Those are the numbers that you're trying to find. And then we still have the square root of negative 1, which is an I. So what's the square root of 4? 2. So this square root of 4 becomes a 2. I would go ahead and bring the I over. And that 10 is going to have to stay underneath the square root sign because you can't do anything with it. So the answer would be 2I square root of 10. The only thing different with 6 is that there's a number sitting in front of the square root sign. So I'm still going to handle the square root of negative 121 the same way that I've been doing them before. So I'm going to write this as 5, and I'm just going to do times the square root of 121 times the square root of negative 1. So I'm just splitting that number apart again so I can get the imaginary unit to come out. What's the square root of 121? 11. And then I have the square root of negative 1 is going to be an I. So really this turns into just a big multiplication problem. So the only things that I really have to multiply are the 5 and the 11. So that gets me 55. And then your I just drops down too. Okay, I want you guys to try number 7 there. So I would have started by splitting it apart so I can pull out the negative 1. Now there's a negative in front of the square root sign. All that's going to do is just attach to your problem. So while I'm going to be working with a positive 96, my final answer is going to have a negative sign in front of it. So one of the perfect squares that goes into 96 is 16. 96 can be rewritten as 16 times 6. And then the square root of negative 1 is an I. So the square root of 16 is a 4. So it comes out front now with that negative sign. So it's got negative 4. And then the square root of 6 has, well, I'm going to do my I first. And then the square root of 6 is going to have to stay. So negative 4I radical 6. Really the biggest difference, the biggest change here is that I unit. Anytime that you see a negative underneath the square root sign, just train yourself to know I'm going to have an I in my answer. Because I can't do the square roots of negatives normally. So we can apply this then if we were actually solving equations. So this comes into what we were doing a little bit of yesterday, like with the completing the square and using that square root property. The difference now is that you're going to be working with the negatives, okay? Because it is possible for these quadratics to not have real roots, to have complex roots. So if I had something given to me like this one, x squared plus 144 equals 0, the first thing that I would do is try to get x squared alone. Like you guys would have done when we were using our square root property. You want it to say x squared equals and all of your other stuff. So I'm going to subtract 144. So I have x squared equals negative 144 now. Then using my square root property, we square root both sides. So what's the square root of 144? 12. And then because it's negative, you got to have an I attached to it. So x is going to be equal to 12i. For the second one, you first have to get x squared alone, but you're going to have to do 2 steps here. You're going to have to subtract 72 first, so that it says 2/3 x squared equals negative 72. Now, to get rid of this fraction 2/3, we've talked a lot about, like previously, especially in Algebra 1 when you guys were there, we talked about how if you're trying to get rid of a fraction, instead of dividing by a fraction, it's always multiplying by its reciprocal. So I'm going to multiply both sides by 3/2. That's going to get my x squared alone. Now 72, you could write that as over 1. So you're going to x squared equals, if I actually take this, you could do a little bit of reducing beforehand, but either way you're going to get negative 108. Now we square root both sides. So I get x equals, so 108 times the square root of negative 1. Now we got to find a perfect square that goes into 108. So one of them that I think works is 36. I could take 36 times 3 to get to 108. And then I have times I now. So what's the square root of 36? 6. So I have 6 and an I, and then the square root of 3. Okay, on the next page I want you guys to try number 3. So first thing I would do is subtract 90. So it says 5x squared equals negative 90. Then I would have divided by 5. So we get x squared equals negative 18. Now you square root both sides. So you can rewrite this so that it's x equals the square root of 18 times the square root of negative 1. What perfect square goes into 18? Or 9, 16, which one of those is going to work? 9. 9 times 2, right? So then square root of negative 1 is an I. What's the square root of 9? 3. So we get 3 and the I, square root of 2. So when we start having complex numbers, there's going to be times where it's not just a singular unit. Like so far you guys have only seen answers that were like 5i, 25i, or like 2i squared of 3, or I squared of 5, or negative I squared of 5, or something like that. There are cases when you've got a complex number that's got a regular number piece to it, and then it's adding or subtracting a complex number piece to it. So they could look anything like this. 4 plus 7i, 2 minus 6i, 3i. Usually if they're written with the two pieces, with the number and then the complex root, the number always comes first. So this form here that says a plus bi, a is talking about a regular number piece, and then the bi is talking about the complex part. 3i is still technically considered to be a complex number in this form. It's just the regular number is a 0. It's like 0 plus 3i. Okay, that comes in handy to know when we start dealing with conjugates, which we won't talk about today. But when we start getting into that, we'll have to remember that if it's just a number like 3i, that there is technically a 0 sitting in front of it. So two complex numbers are equal if and only if their real parts are equal. So that would be like the a pieces, they have to be the same number. And if their imaginary parts are equal, so the bi, please. So if you had like 2 plus 5i, that is only going to be equal to something else that says 2 plus 5i. They have to look exactly the same. If they don't, then they're not considered to be equal. We can use this to help us solve equations that have real number pieces and complex number pieces. So if we look, we have 4x plus 10i equals 8 plus 2y times I. So I know there's a lot of letters happening in this. We've got x's, we've got y's, and we've got i's. Okay, so when we are trying to figure out how do we set these up to solve our equations, we look for the pieces that don't have i's, and we look for the pieces that do. And those are the things that you set equal. For example, 4x does not have an I. And on the other side of the equal sign, 8 does not have an I as well. So we're going to just take those two pieces and set them equal. 4x equals 8. Now if I wanted to solve for x here, because they're asking me to figure out like what's x equal to, I'm going to divide both sides by 4. So I get x equals 2. Now if I look at the other pieces, so the 10i and the 2yi, those two pieces there, they have i's attached to them. So I'm going to set 10i equal to that 2yi. What really can happen here is because there's an I on each side, they can cancel each other out. So I'm just going to go ahead and just mark them off. So I'm left with 10 equals 2y. Then I divide both sides by 2, and I get y equals 5. So if I took my x and I took my y now, and I plugged it back in up here, so I'm just going to do this above the problem. 4 times x, so that'd be 4 times 2 is 8, plus 10i. Now on the other side I have 8 plus, it's 2y, so 2 times y, 2 times 5 would be 10, and then there's an I. So I did get 8 plus 10i, 8 plus 10i, after I plug my x and my y values back in. So they are equal, which is why we're able to do that. We're able to solve for x and y to figure out what do they need to be in order for these sentences to equal each other. Okay, so let's do another one together here. So I have 4 plus 2i equals x plus 4yi. 4 on the left side does not have an I. What piece on the right side of the equal sign doesn't have an I? The x. Okay, this one's going to be pretty straightforward. 4 equals x. That one's solved. Okay, that one was easy enough. So then the other pieces, 2i, 4yi, those get set equal to each other. And if you guys can understand that because they both have i's, that those i's cancel, I'm okay if you just drop them off right away. And you just take the 2 and you set that equal to 4y. So if you want to drop them off right away, that's fine. So then I'm going to divide by 4 on each side, and I'm going to get 1/2. So again, if I went back and I actually plugged in my x and my y up here, I don't really have to do anything to the right side because it's just 4 plus 2i. But then we have x, which we said was 4. And then we have 4y, so that'd be 4 times a half, or 4 divided by 2, which is 2i. So again, they match on either side. When I actually plug in my x's and my y's, I get 4 plus 2y on both sides. So if you guys turn the page over, there's one more that we're going to do today, like those problems. I want you guys to try it. All right, so this one's just written backwards because they've got the I part first. So you've got negative 4xi. What would you set that piece equal to on the other side? Good, negative 10i. That means that the negative 20 and the 16y should have gotten set equal to each other. So I'm going to do the negative 4x, set that equal to negative 10. I'm just dropping the i's from both of them. I divide by negative 4 on both sides. So I'm going to leave it as a fraction. I'm just going to reduce it. First of all, it becomes positive because I've got a negative over a negative. And then I can take a 2 out of both. So I get 5 over 2 for x. For my y piece, I'm going to do negative 20 equals 16y. Divide by 16 on both sides. What's a number that I could take out of that fraction? 4. So then I would get negative 5 over 4.